Okay, welcome everybody. How's it going? Whoa. Okay, what's going on? You had what?
Homework and test in the same week. It'll matter.
Is that supposed? You're telling me that we have homework and a test in the same week here?
Yeah.
The test was earlier, right?
Yeah, right.
And now the test is gone.
Yeah.
And the homework's due.
Yes.
Yes.
That's a problem. That's a little great.
All other midterms.
All right. I am hearing. Okay. So this is what we'll do about that. All right. I want everybody to work as if it's due today at 7 p.m. All right.
That's crazy.
Then, what do you mean that's crazy? Wait, what? It's due at 7. All right. And if you're opposed to me extending the deadline, okay, please send me a private message in Canvas, okay, and then after, right, so I'm sure many people are not opposed to it, right, but if you think that's unfair, all right, send me a private message, and then I will evaluate whether or not we move the deadline. The deadline, right, if I move the deadline, right now it's at 7 p.m., but if we do move the deadline, like till tomorrow or midnight, okay. Oh, you want midnight? Oh, okay. Well, midnight is tomorrow, right? Okay, no. Okay, so, right, so if we move it, right, and then whatever happens, right? You're not going to be penalized, right? But it takes me a few minutes to do that. I'm not going to do that in the middle of class because I have to go through each individual problem and extend it for everybody, right? So I'm getting that a lot of people like an extension, all right? If you have reason for saying why we shouldn't have an extension, send me a private message and I'll take a look, and then by 8 p.m. you will have an answer, okay? All right, but you want to work like it's due at 7 p.m. All right, is that fair? All right. Now, now I just asked you to work like it's due at 7 p.m. and I'm supposed to teach you something in this next couple hours, right? And just for anyone who's joining us, this is not completely unjust. This assignment was assigned a week ago, right? So it's been a week, just so we know, right? It's not like it was assigned 2 hours ago. All right. So what we're going to do today is a couple of examples, kind of under the mode that maybe you've looked, although it sounds like that's probably not possible, but maybe you've looked at what's happening in session 11, all right? And then maybe the examples will be a little bit of a clarification. All right, so session 11 is our return to beam bending. Okay, so this is beam bending. What? All right. So there are 4 equations that come out of this session, okay, that are big. And maybe some of them you already knew, maybe some of them you didn't know. All right. The first is a relationship between the change in shear force inside a beam versus the distributed force being applied to it transversely. All right, so this is given as dV dx equals W. The second equation is dm, so the change in the internal moment, and how that relates to the internal shear force. And then we have a concentrated force, okay, concentrated force F, and that can be related to a step change in the internal shear force, And we also have a concentrated moment app, and that can be related to a change in the internal moment. Just a couple of things to note here. We do have a convention. I won't go through that. That's in the notes. Okay, I won't go through it in detail. But this F, a positive F, if you're going along the beam, is up. That's positive F. Okay? This is counterintuitive. A positive M app is actually negative, right? By right-hand rule, that's going into the board. Now, I have a question for you. When we say right-hand rule, all right, I was talking to someone recently, and people were saying that we don't use analog clocks much anymore. All right, so when you think right-hand rule coming out of the page, and someone says counterclockwise, do you think of a clock first, or do you think of the right-hand rule first? Because we don't use analog clocks much. Clocks. Okay, so some people still use analog clocks. Okay, that's good. All right, just checking. All right, but some people, it's fine if you think right-hand rule. All right. Okay, so there are a couple examples that I'd like to do that kind of share a little bit of a process that you could apply here. Now, there are a couple ways you can do these problems. One is you go old school back to statics, and you just do it like you did in statics, which is method of sections. But what we're trying to show is that there's kind of another way that uses these equations that we've just described, partially. They're not partial derivatives, though. Anyway. No joke. All right, so we're trying that we use what's called a graphical method. Okay, graphical depiction. All right. So let's see about this problem. Okay, this is L. This is L. This is a wall. All right, that's our beam. So step one, with either of these techniques, it's not bad to create a model. All right, so what's the model look like? Typically, this model is going to be something that we use for external equilibrium. All right, so I'm going to go ahead and put the external forces on here. And then I'm going to look at the constraint and say, I'm going to have a reaction force, and I'm going to have a reaction moment. And I'm going to call this reaction moment MR. Okay, reaction moment. Here, there's no convention being employed at this point. So we are looking at picking an R and an MR that should be convenient for us. Okay, so MR is in the clockwise or counterclockwise direction, and that should be opposing what is being applied by these two external forces, P. Then another thing that's often good to do is external equilibrium. So let's look at external equilibrium. Okay, and if we do this, we're going to look at the sum of the forces being equal to 0, and we're going to look at the sum of the moments being equal to 0. Okay, so sum of the forces for that, let's say that we have positive R minus P equal to 0. So R is equal to 2P. And for the sum of the moments, let's pick a spot. We'll pick it right here, A. So we're going to say we're going to do the sum of the moments at A. And that is going to give us let's say over here, that's going to give us a positive MR, okay, and a minus PL and a minus P times 2L equals 0. Okay, because this distance here and that distance there is L. Okay, so MR is equal to 3PL. what do we do at this point? Well, we can begin to think about what's happening at the ends and boundary conditions as we employ a graphical method. So let's say we want to do a graphical technique. Okay. So it's not bad to just go ahead and draw a couple of graphs that are blank, like this. Whoops, what am I doing? This is X, this is V, this is M, okay, like that. And now what we can look at are boundary conditions. So let's look at the boundary conditions. What does that mean? That means that you take a little sliver at the left or the right end of the beam, okay, and think about what is happening just inside the beam. So you just moved a little bit away from the boundary, from the constraint. So in this case, if I look at the left side, I've got this little beam and this little chunk, that's a cut. I have my R over here. I have my MR over here, okay? And I've got my internals, and these do follow the conventions, okay? So what is it here? I have an internal force, shear force down, and I have an internal shear force, or internal bending moment that's helping make it smile. Okay, so what I see here, I calculated out, right, that this R, I already calculated out R and MR, all right, from external equilibrium, all right, they're right here. And so what this means is that at the left side, V has to be equal to R, so V equals, okay, so V is going to be equal to R. And also that M is going to be equal to minus MR, okay, so M is equal to minus MR. So what I do is I go over to my plot and I'm like, oh, well, so V equals R. V equals R, that means that V equals 2P. And I just say, oh, I'm going to say this right here is 2P. Right there. And M is equal to minus MR, so that's minus 3PL. Okay, and I'll put it down here. Okay, so I've got these points now. What do I do? What do I do? Well, this is where I employ the equations. I have a dV, I'm going to use a different color just because that's fun. I have a dV dx is equal to W. Okay, W is a distributed force. All right, transverse, there's none, okay? There's this W, this is equal to 0. So what does that mean? That means that the derivative of V with respect to X is also 0. What does that mean in terms of what the geometry or what I'm graphing? Yes? Yeah, it's constant, all right? And I know there's another something happening at L, so I'm going to draw that constant something only up to the first L, okay? Because we're going to go to 2L in this particular case, okay? So what happens is up to this point, it's flat. Now, let's write the other equation that is often useful. dm dx is equal to v. So that means that m is equal to the integral of v dx, okay? And v is a constant, okay? V is a constant, all right? This is a constant 2p. Okay, at least for the first region, for the left portion. Okay, so what does that mean? That means that I have a slope, right? So this is a flat, and now I have an integral of a flat line. That's going to be a first order line, right? So that's going to be something with a slope, and I know it has slope at 2p. If I go over L, so if I go to the L and I have a 2p slope, right? That means that L, right? That means that I'm going to go up 2pl. So at this location, I'll be up 2pl, which means I'm at minus pl. And I get to that location, and it's a nice line. Okay? Now, what do I do once I've gotten here? Well, I get scared. All right, what am I supposed to do? I'm not sure what I'm supposed to do. Well, let's look. I've got this other equation. If I have a concentrated force, then it's equal to a delta V. All right, that concentrated force can be in the form of this P, or this P is a concentrated force, but it's in the opposite direction as this positive F. So that causes a drop, a delta V of P at that location. So that means I go from 2P down 1P to P. All right? So now I'm at P. And I go back to this equation, and it's dV dx is equal to W. W is still equal to 0. There's no distributed force in that region. So that just stays constant. So I'm going to end up at P. Another flat line. Okay? So that graph is done. And if we were to look at the boundary condition on the right side, what do I mean by that? If I were to do an internal slice on the right side, okay, extra, read all about it. Okay, if I do a slice on the right side, I've got this P going down. Now I've opened up this side to the left, which means that by convention, because that's internal, this is what it should look like. Guess what? V equals P on the right side. We've satisfied that boundary condition. What's going on over here? This one's a little more complicated. I have a step change in height, but I don't have an applied moment, a concentrated moment. So I don't have a discontinuity in the actual, like I don't have a jump, all right? But look, the slope has changed. It went from 2p to p. So what do I do with that? Well, I think, okay, now I've got a slope of p, and I'm going another L. That means I'm going to go from minus PL, and I've got a slope of P, and I'm going L. That means that distance 2L minus L, that's the L, right? So then that gives me a slope here of well, I already said the slope was P. That takes me down from PL, or minus PL, or takes me up from minus PL to 0. Like this, and we'll just do it in a different color. So we end up at 0, and the slope is less. It's P instead of 2P, just like that. And once again, extra, read all about it. We have this boundary condition that we can look at. What is M? Well, there's nothing on the right side. It's 0. So M is equal to 0 on the right. Okay? Which means we're satisfying that condition as well. Okay? So, do you want me to do another one of these examples, or do you want me to be quiet? Yes, Kevin.
Could you explain one more time how exactly you split up, or how you method of sections the reaction force, and you're able to determine and then model both the shear force and the shear moment? I'm a little confused on why M is equal to negative MR. Or more specifically,
This
why,
one.
Yeah, more specifically, why it's important to model it.
Okay, because look, I might have skipped a little thingy here, right? When you have this equation, dm dx equals v, or you have this equation dv dx equals w, or omega, all right? You've got to do the integral of both sides. But this is an indefinite integral. So an indefinite integral, right, has a plus c, a constant. We don't know what that constant is. That's why we have to use a boundary condition. Okay, so we had to use the boundary condition, and the way to use the boundary condition, the simplest way, or the way here, is for us to look at what is happening internally just next to the left side, or just next to the right side. Okay, because I already solved for external equilibrium, which tells me what's happening at the left side and what's happening at the right side. Okay, so that's why we're looking at what is V, and this is a BC at left side. Okay, and so my little squiggly right here is supposed to signify that I've cut it right there. I'm using the method of sections, and there's not much distance that's gone from here to here, so I can essentially say, hey, R is going to be V, and M, or however you want to look at it, plus MR minus, or plus MR plus M is equal to 0.
Okay.
So since, right, that's what maybe I skipped that step a little fast, but M plus MR is equal to 0.
So in this situation, from the boundary condition, you determine the direction of M from just the diagram?
Yeah, just from the diagram.
But
That's it.
You get the magnitude of M from the integral.
I get, if I'm using purely graphical, I get the derivative from this expression, okay? But if I'm, and then I can actually solve out for this expression if I plug in the boundary conditions, and I can actually get the actual expression for this part of the line, okay? But it's a little bit dicey, because sometimes if you start from here, that's a different, like if you're going from the middle and going to the right, that gets a little bit tricky, because you had to account for where you're starting again, okay, when you solve for these intervals. But the point is that one of the points is that these two equations allow us to figure out what the slope of V and the slope of M are as we go from one region to another region. And we go until we hit another constraint or we hit another external load. Okay? Do you want to do another example, or do you want to work on your homework? What? Work on your homework? Okay. The other example is, actually it's pretty much done in the notes as well, but maybe a little faster than I did this one. Actually, it is quite a bit faster than I just did this one. But the other example, if you're interested, that we skipped, okay? So example to chew on, to think about. I don't like ending a phrase with a preposition, but anyway. It's this example where you have the like that, and there is a moment applied in the middle. Okay. All right, I'll go around. Praj, you're here, right? Yeah, Praj is here, so we'll go around and we can answer questions on things. All right? Good. What's that? Okay. This is not a pen that's useful. Are you out? You out? You got questions?
I just studied.
Right. So all right. Good. Okay, there's a question about pre-po-max. Okay, you're given the shear modulus, right? Given, is this question number 7? What question is this? The 7? Okay, so this is pre-po-max session 10, question 7. All right. When we give the shear modulus. Okay. But most FEA packages don't say what's the shear modulus. What do they ask for? What are the open boxes for pre-po-max? Okay, so the FEA package wants to know elastic modulus and Poisson ratio. It also might have wanted a density too, but at least it wants these two, right? So what's the relationship between these? What's the relationship for an isotropic linear elastic material? Yes? Right? That's relationship. So you're like, well, wait, so what do I do? Because you didn't give me a Poisson ratio. You didn't give me elastic modulus. Just pick one. All right? So just pick, something 0.2 to 0.4, right? 0.3 is a good option. All right? And then figure out what the E is associated with this and do the problem. Yes? Okay. All right, so look. If you go to, I tried to talk a little bit about this and I guess the last week, right? It is very confusing to know which shear strain you're interested in, right? Is that the question? And then relating the tensorial shear strain in pre-po-max to our general definition of shear strain. Okay? So first, there is a factor of 2 in the magnitude. So if you're looking at one of the shear strains in pre-po-max, okay, what you'll see is that you have E, right? You have the E's, and you're looking for off-diagonal terms. So E12, E13, E23, right? Those are your options. Not for the normal strains. These normal strains, they work out nicely. But for the mathematics to work, with the tensors and things that it's solving for, what you have is a factor of 2. So pre-po-max, right, is going to give you this E12 value, but then you have to multiply by 2 to say get a gamma XY. Okay? Does that make sense? That's for the magnitude contribution. So if you decide that you want to know gamma XY, you're going to look at E12, all right, because X is the 1, Y is the 2. You're going to look at E12, and then you're going to multiply by 2 to give you your gamma XY. Okay? Now, the question is, which one should you be looking at? Should you be looking at gamma 1,2, gamma 1,3, or gamma 2,3? Well, it kind of depends. All right? It kind of depends. And that's what we were trying to get at here the last time. If you're on the top element, right, and you have the y coming through it, like here, that means that x is to the right and z is down. Do we see this top element is mapped over here? Yeah? Okay, so in that case, if I'm thinking about the shear stresses, right, so normally or I'm thinking about the shear strains, either way, this is on the x face, and down is positive z. Okay? With the way this is drawn. You may have decided to use a different coordinate system. If you did your cylinder along the z-axis, it's going to be different than this. Right? I did my cylinder along the x-axis in this case. If I'm looking at a side element, so if I'm looking at this thing from the side and now z is coming out of the middle of the element, then I'm looking at an x direction over here, a y direction over here, okay? And upward would be positive tau xy, okay? But this is negative. This is downward. Why is it downward? It's because, we've talked about this a little bit before, if I were to draw a rectangular grid, first I have a rectangular grid that's really nice. Well, that's not very nice. Okay? But then I twist it. And let's say I twist it with a torque like this. Okay, so I've got a torque that way, and I've got a torque this way, because it's got to have a reaction torque on the other side. What's going to happen to the grid? The grid is going to go from this nice rectangular with right angles okay, to something that looks like this. Okay. Right? So what you're seeing is that these sides have gone down, these sides have gone that way, just from deformation. That's with twisting, right? If I had if I was a better teacher, I would have a nice rubbery thing that I'm twisting. If you want to see, this in action, watch Jeff Hansen. He gets a pool noodle out, right? And he has this pool noodle, and he twists it, and you can see which direction the pool noodle is twisting. All right? Okay? So that's how I know that on this side, on the right side, I have it going down, and then on the left side, well, once I know one of the shear stresses, then I know them all. Okay, because this one has to be counteracted. The arrows hit each other. The arrows hit each other. Okay, so this bottom one has to hit this one, and this one on the top has to hit this one. Once I know one of the sides, I know all four. Does that help? Maybe? Okay, I'll come over. Were there other questions, general questions about pre-Pomax and the finite element? Okay. Okay, that's all right. Okay, so this is okay, that's wild. All right, which is okay, I'll close it. Yeah, okay. Actually, we just spin it around. Yeah. There we go, right? So now, let's kind of go through this. Okay, right, so now, let's take this top. Which, if I look at why is it out of the top? Right? This could be like, this could be like this example right here, the top, right? It's the same. So on the right side, we're looking at this text. Okay, really at the top. So if you put a query right there. So you
So
write
is J just equal to pi over 2 times outer diameter with power over
and then this,
pi over 32?
Oh,
That makes sense. Wait, L squared?
So, yeah, that's, it's kind of right here, you should be this but, so it's gonna be a little bit off, right? But, if we look there, now let's go back.
So that's, what is
Because
this,
that's what we have,
5?
right, without, for you. So that's the screen right here, that's what that is. Oh, that's way off. How could you come 8 times? I was expecting like really small, right? This is a huge amount. Alright, so let's do your
Yeah.
Okay, so.
Okay, so he does the same thing. J's the most
No, that's
he does just your
That might be why we're off. Because it's
Remember
big.
what?
Yeah.
Oh yeah, you're not calculating.
Okay, so we want to, let's go back. I don't know exactly, so let's go back to the.
But I'm struggling with J, because I don't know what C is. Which one? C? Oh, I did. Oh. No, I did minus. I did minus. Yeah, I did. That's not working.
Oh, no.
Same thing. That's what I did.
I have no idea.
So it's asking you what
Yeah. So, no, yeah. So this is what I've got. I mean, I'm pretty sure it's right. I just don't know where I'm messing up. So that's the It's a dynasty. Oh, this is radiant.
whatever you get, 180 by 7.
It gives radiant.
Yeah, yeah. So you
I just need to
okay, yeah, that's more like it. So that's.
It doesn't make sense. Why would you ever this?
Right, so because that value compares to you. Oh, yeah, there's
I know. I'm saying what is C? Is C obvious? And how do you know that?
Question? Okay, yes, I'll be back. Yes.
Wait, I can't.
You can ask me a specific question. Okay, so we wanted to ask you, so again, ask a specific question. Okay, so there are two relationships between you. Right? One is and the other is and you will that feel the amount that it rolls on are and if you have another wheel, that's also wrong. So what happens is if the wheels are exactly the same size, then if you rotate one and one at a time, you rotate the other. If they're not the same size, then you have to rotate R1 R2 your R1 data 1 equals R2. So that's the first relationship. And of course, these thetas are in opposite directions. And you don't want to solve that. Usually with externals, we don't have to use anything out there. In the size, that's what it's the other thing is if you look at contact. The force, you have a force of one gear acting on the other, and then you have an equal opposite force of acting on the third. So which is not restricting force, just or so then what you have is right, you have you also have a source of biases by a force at a degree. So you really get to draw that. You guys are not just
Go back to
This is going that way, right?
scroll down.
Now, let's say, I'll say that I also have longer time. Alright? So you look on R1.
One of them is
Did you do dessert? Times 180 divided by
And the other two right is R1 here. And that's that concrete. I couldn't name names.
Oh, okay. Okay. But it's whatever it gives you, right?
You're actually there for your.
Right?
You got it right. Hold on.
I'm in the middle.
What did you do?
We just found things. I did that. I keep getting it.
I used to just I found the top part.
Yes, I could just probably go back, right? No, because
Oh my god. It took me so many tries. You gotta be really careful for your like calculations.
And now, you look there.
yeah,
Start over there.
Straight, 2 times.
I'm sitting here like.
Hello, everybody. If you're working on the pre-POMAX question 7, all right? The first thing you want to do before you even put it into the finite element is calculate out what the alpha is, or the gamma is, okay? That's what you want to calculate out. That's the answer that goes in the box for what is the maximum shear strain, right? The TC over JG. After you have that value, I mean, don't submit yet, right? Your goal then is to make sure that you have pre-POMAX telling you whether with an E12, an E13, or E23, depending on how you define your cylinder, that value, that max E12, like when you do a query on it, you should have to multiply it by 2 to get the value you got over here. Okay? So whatever the E12, E13, E23 is half what the value is for the actual gamma. Does that make sense? I've seen a lot of people doing this, and they're looking for the right number, but they didn't calculate out what the actual number is. Just using the TC over JG. Okay? Any questions on that? Okay. Good.
Damn, how much is that?
You're just mad that you did it.
switched out.
Yeah, it's up. It's up right now, yes.
Very large
Like,
number.
in regards to the people mass.
73.
Everything I've said is up, yes. Yeah, it's up. Okay,
So like,
let's see here.
I tried doing it two different ways. One way gave me a negative answer.
Hold on,
And the other
hold
one
on,
gave
just
me
one
a very
second,
large
all right?
answer.
Okay, here's the attendance, and I'm gonna be clear today. Take a picture of this now. I wanna be nice, but the number of things of people sending me late attendance has gotten to a point where you gotta take a picture, you gotta submit it on time, all right? Tell me if there's a technical issue before you leave the classroom, not in an email, all right? Extra credit?
For it, yeah.
No, because you're actually doing attendance and reporting it correctly.
Extra credit for those who actually call.
You get attendance. That is your credit.
Extra credit is what I'm saying.
So let's ask a question. In an equitable class, is there anything as extra credit? In an equitable class?
Yeah.
Yeah, you should do it.
How can there be extra credit if everyone is given the problem?
You do a bonus. Yeah.
But everyone's given the bonus problem, and you sum all the points at the end of the semester. Does extra credit exist?
Well, the people that don't do it don't get it.
Yeah.
Right. So that's like assigning another problem for everyone to do. And I can call it extra credit, or I cannot call it extra credit. It all is the same.
Yeah.
But if everyone else gets it right.
The solution?
good if I don't do it right now.
My laptop's dead, so I can't even do anything.
And it's like, I swear.
That's not how I did it.
As of right now, I still do tonight.
Mechanics materials. I think it's a difficult class, but I like it.
All this stuff makes sense.
Yeah, it does. At least it starts.
There's a logical, like, pathway to it, which I appreciate.
Like this.
But, okay.
Right. Well, that's
Look who is talking. Oh my god.
exactly.
Okay.
That's what I was trying to explain. Honestly, I'm not even.
Tears.
You got 3 good things. I'm not doing
I can't even do the math part of it.
I'm gonna freak out and freak out next. I can't even read it. That part.
I do the math.
Well, so this is, you divide by 2.
Yeah. That's what it works.
I think I knew what I was doing. Okay, so we're done. Yeah. It's cool.
Well, to 5 years, 2 years.
I'm just
Oh, I can scale it. Thank you, thank you.
not
Then if you look good, look at the map, only look at the map. This is the max one, is one to
Like I have this like time thing. I don't know. That's like you want
For 2 points, that's gonna take like 20 minutes. So, yeah, if he does, I might do it. Depends on how long he's
we gotta go back to the okay, let me just
I'm done.
Wait, the polar one piece?
Well, I essentially skipped it because.
Essentially walked around the hard part of the problem.
Yeah, exactly.
Right, and that's, remember, we do that in class. Okay, and so we add those angles up, right? So there's an angle from here, and there's an angle from there, right? They're both at here, and that's the total angle with A or C. Right? Is there any changes? Is there any more to it? There's no idea. It's just a long ride. Okay? So now we figure out what the time rule is. We figure out what right? We figure out and now we figure out quick thing. Alright. Now right? To give me same. Zero. Okay? And in this case, it's close.
There's supposed to be times 2.
Right, it's just a huge shaft, it's a very long shaft. Okay? So then,
Oh, it's point double O one.
this one?
Yeah. No, it's not. 0.00.
Alright, now go down, right, so that's the first thing to figure out, so then we go further, and
And then
we
you
have
have to
other out.
apply it close with a mesh and then change the limit per curvature.
So, okay, so you figure out what?
And then these two.
And so say,
And then the bottom is 0. I'm pretty sure it's
I have this now,
the guy's name, Fang.
that, yeah.
Wait, so I.
So I can apply that reaction for.
Once he's done, you can help me. But that's all. That's as far as I got.
Clockwise or counterclockwise, minus counterclockwise. It's counterclockwise and minus the clockwise.
Keeping them plugged, dude. You got a dollar for it.
We're out now. We're out.
I can keep it going.
I just that message.
Go fuck both of them you.
You need to go back. We got another court, right? And it also requires that you, that we, so you have to go into the,
Alright, let's
all right, good luck. Good luck.
Professor Mateo, have a good evening.
Okay, is that an intense line?
That was no too much enjoyment of neck materials.
We celebrated
Yeah.
It was a great day, guys.
Yo,
I didn't cut it this way.
You're more than welcome to use the brief room.
Okay, yeah, what about it?
Alright, let's.
Is it around to receive?
We'll be there.
I'm good to receive. Please start.
Well, yes, because, it's got 15 years. So it hasn't been transformed.
I already did the transfers, maybe.
Well, it's not, that's not 2 years.
Yeah, no, maybe.
Take that.
Should we just?
Yes.
You said it crashed.
Did you figure it out?
Computer like.
You did? Why did it work?
This took me.
I couldn't get
It's Peter Campbell.
Yes.
For one, like, someone came up with it, like,
Do you know how No, but like for
You have to do a reference point, and then you lost.
yeah, why?
Where's your phone? Yeah, but is it like, is that like as a load or?
Oh, okay.
So usually you want to, where to go? Yes, sir. What do you think, Mark? Yeah, don't bring in the second target, I don't know. Just start over and go slow. I don't know. I don't know, I turned my head for 1 second, and now you got 2 points there.
Maybe the first one was about
Okay, now let's go to page. Let me see, is it okay? So you can see. Okay, that was fine. Geometry. Or the next one. No, not there, there, yes. Okay. And then go view. Yeah. So now that. Oh, those are files. So I would do like, usually I would do like. Here I would like 20 or so on. And then for the math on side, I would do more like 0. Because that's 3 millimeters. I mean, you go through, you can also do that for a while.
So we do get the time extension.
I'm gonna check my email and then I'll make a decision.
All right, if anyone's still here for the video, just a note, the what was asked in the problem set, I was mistaken earlier. It was actually asking for the tensorial shear strain. That's what I asked for. I thought I was asking for the alpha or the gamma, but I'm actually asking for the tensorial shear strain.